Have you ever wondered if time could just stop? It's a question that has fascinated scientists, philosophers, and dreamers for centuries. We experience time as a constant, always moving forward. But what if that flow could be interrupted or even halted altogether? It sounds like science fiction, but in our universe time can nearly freeze under extreme conditions. The cosmos is full of places where the rules we take for granted are bent, twisted, or even broken. In certain places like near black holes, the flow of time is stretched to an unimaginable degree. These cosmic monsters are so dense their gravity is almost beyond comprehension. Imagine a clock ticking so slowly that billions of years pass for us while only a second passes for it. To us it would seem almost frozen, as if time itself had been put on pause. This is a consequence of Einstein's theory of space-time. Gravity and time are deeply connected. Einstein showed us that time isn't just a backdrop to the universe, it's woven into the very fabric of reality. The stronger the gravity, the slower time flows. This means that time ticks differently depending on where you are in the universe. This isn't just theory, it affects satellites, distant galaxies, and even the light we see from space. Our GPS systems, for example, have to account for these time differences to work accurately. So can time actually stop? To answer that, we need to understand gravity's effect on time. The deeper you go into a gravity well, the slower your clock runs compared to someone far away. Einstein described gravity as a curvature in space-time, not just a force. Massive objects bend the fabric of space and time, creating strange effects. Massive objects like black holes warp space-time so much that time itself slows dramatically at their edges. The closer you get, the more extreme the effect becomes. At the event horizon of a black hole, the laws of physics are pushed to their limits. Here, the boundary between what we know and what we can only imagine becomes razor thin. Here, time nearly stands still for an outside observer, setting the stage for one of science's most profound mysteries. The universe's ultimate stopwatch may be ticking, but at the edge of a black hole, it's almost as if time itself holds its breath. To truly grasp the nature of time, let's talk about Einstein, the man who forever changed our understanding of the universe. Before Einstein, Isaac Newton imagined time as absolute, a universal clock ticking away, the same for everyone, everywhere, no matter what they were doing or where they were in the cosmos. But Einstein's theory of special relativity shattered that comfortable idea, revealing that time is not as rigid as we once believed. He showed that the speed of light is always constant no matter how fast you're moving. Because of this, space and time themselves must be flexible, able to stretch and compress. Space and time are woven together into a single fabric called space-time. Your experience of time, how fast or slow it passes, depends on how you move through this fabric. For example, if you travel near the speed of light, your clock ticks more slowly than a clock back on Earth. This strange effect is called time dilation, and it's been proven by experiments with fast-moving particles and even airplanes. Einstein's general relativity took things even further. He realized that gravity isn't just a force, it's the curvature of space-time itself, caused by mass and energy. This means gravity doesn't just bend space, it bends time as well. The stronger the gravity, the slower time flows. So if you're near a massive planet or a black hole, time actually runs slower for you compared to someone far away from such intense gravity. This isn't just a wild theory, it's something we can measure and use in our daily lives. For instance, GPS satellites orbit high above Earth, where gravity is weaker, so their clocks actually run a bit faster than clocks on the ground. If we didn't correct for this difference, your GPS would quickly become wildly inaccurate, sending you miles off course. So, gravity's effect on time isn't just real, it's measurable, and it's absolutely essential for the technology we rely on every day. Einstein's insights didn't just transform physics, they changed how we see our place in the universe. The flexibility of time is not just a scientific curiosity, it's a fact of life, woven into the fabric of our modern world. And nowhere is this mind-bending effect more dramatic than near a black hole, where time itself nearly comes to a standstill. Let's break down gravitational time dilation with some real-world examples and see how gravity's invisible hand shapes the very flow of time itself. Imagine two friends, one standing on the ground floor of a towering skyscraper, the other relaxing in the penthouse suite high above the city. The friend closer to Earth's center, where gravity is just a bit stronger, actually ages a tiny bit slower than the friend above. It's a difference so small, you'd never notice it in daily life, but it's there, proven by science. The effect is minuscule, but with incredibly precise atomic clocks, scientists have measured this time difference between floors in tall buildings. Even a few meters of height can make a measurable change. Now, scale up to the Sun, a place with much stronger gravity than Earth. A clock placed on its surface would tick noticeably slower compared to one here on our planet, and the difference becomes much more significant. But let's go even further. Consider a neutron star, an object with more mass than the Sun, squeezed into a sphere no bigger than a city. Its gravity is so intense it warps time in ways that are hard to imagine. Near a neutron star, time slows dramatically. If you could stand safely on its surface, you'd experience seconds while years might pass elsewhere. An hour spent near a neutron star could mean months or even years pass on Earth. The stronger the gravity, the slower time moves for you. As mass and density increase, gravity's effect on time becomes extreme, stretching and squeezing the fabric of reality itself. Planets like Earth barely bend time, but neutron stars and black holes create deep dramatic wells in space-time, where time nearly stands still. This progression leads us to the ultimate time bender, the black hole, where gravity's pull is so powerful, not even light can escape. Here, gravity's grip on time is absolute. At the edge, known as the event horizon, time appears to freeze from an outside perspective. What happens at the edge of a black hole is the most extreme example of time dilation in the universe, a place where the rules of time as we know them break down completely. Black holes are the universe's ultimate gravitational traps. When a massive star collapses, it forms a singularity surrounded by an event horizon, the point of no return. For an outside observer, anything approaching the event horizon appears to slow down, its signals arriving further and further apart. The object seems to freeze in time, its image fading as it nears the edge. This is gravitational time dilation at its most extreme. From afar, time at the event horizon appears to stop. But for the astronaut falling in, time feels normal. They cross the event horizon in a finite moment. The outside world, however, would never see them cross. They'd appear frozen forever. This paradox is a hallmark of black hole physics. Two perspectives, both valid but wildly different. It's a mind-bending consequence of relativity. The difference between what the distant observer sees and what the falling astronaut experiences is at the heart of relativity. For us, the astronaut's time slows to a stop at the event horizon. For the astronaut, time flows normally, while the universe outside speeds up dramatically. They might see the future of the universe unfold in moments. There's no universal clock. Every observer's experience of time depends on their gravity and motion. Both the astronauts and the observer's clocks are correct in their own frames. Gravity warps space-time, diverting motion from time to space, slowing clocks near massive objects. So is time frozen at a black hole's edge? It depends on your point of view. For us, yes, objects appear frozen forever. For the falling object, no, time continues as usual. This duality is one of the most profound lessons of Einstein's universe. Black holes aren't the only places where time gets weird. Physicists have theorized about white holes, the opposite of black holes where nothing can enter, only escape. If they exist, time near them would be distorted in reverse. Neutron stars, with their immense gravity, slow time by about 30% compared to deep space. Pulsars, rapidly spinning neutron stars, let astronomers test relativity in extreme conditions. There are even more speculative ideas like cosmic strings, ultra-dense one-dimensional defects in spacetime. These could, in theory, create closed time-like curves, paths that loop back in time. The expansion of the universe also creates cosmic horizons, beyond which galaxies disappear from view, their light red-shifted away. These phenomena show that time's flow is shaped by the universe's structure and energy. Wherever gravity or motion is extreme, time bends. The cosmos is full of places where time refuses to behave. How do we know time dilation is real? Experiments and technology prove it. The Pound-Rebka experiment in 1959 measured time running faster at the top of a tower than at the bottom, just as Einstein predicted. GPS satellites orbit in weaker gravity and move fast. Their clocks gain about 38 microseconds per day compared to Earth. Without correcting for this, GPS would be useless. The fact that your phone can guide you is daily proof that time is relative. Astronomers see gravitational redshift in stars orbiting the Milky Way's central black hole, light stretched as it escapes intense gravity. The Event Horizon Telescope's image of a black hole's shadow visually confirms space-time warping at the edge. These observations match Einstein's predictions. Time dilation isn't just theory, it's measured, observed, and essential for modern life. The universe's ultimate stopwatch is ticking all around us. So does time ever truly stop? According to relativity, time slows asymptotically near a black hole's event horizon. It gets closer and closer to stopping, but never quite does from our perspective. For an outside observer, the falling object appears frozen forever. But mathematically, the clock never reaches absolute zero. It just ticks infinitely slowly. The universe prefers infinite stretching over true standstills. At the event horizon and singularity, relativity and quantum mechanics collide and our current theories break down. New ideas, like the holographic principle, suggest the event horizon might encode information in ways we don't yet understand. Perhaps time doesn't stop, but transforms into something else at these boundaries. We need a theory of quantum gravity to know for sure. Until then, the question remains open. The edge of a black hole is not just a boundary in space, but in our understanding of time itself. So is time frozen somewhere in the universe? From our perspective, yes, at a black hole's event horizon, time for a falling object appears to stop. This isn't science fiction, it's a prediction confirmed by experiment and observation. But the person falling in experiences time as usual even as the universe outside races ahead. Time's flow is local and relative, shaped by gravity and motion. Our technology, like GPS, depends on this strange truth. There is no single universal now, every observer's reality is unique. The event horizon is a boundary in both space and knowledge. It challenges us to seek a deeper theory of time and reality. While time appears to freeze in some cosmic places, the true nature of time remains one of the universe's greatest mysteries. The quest to understand it is far from over.